You know those shortcuts you use every day on your computer? Super convenient, right? They save a ton of time. But what if that exact same feature, something we all trust, could be flipped on its head and turned into a weapon? That's exactly what we're diving into today.
Yeah, let's just put it out there. What if a simple file shortcut could literally be a weapon? I know it sounds a little dramatic, but this isn't science fiction. It's a real, decades-old headache in cybersecurity. We're going to break down exactly how something so helpful can be made so devious.
Okay, so how does this actually work? Let's paint a picture. Imagine a totally normal program, maybe your antivirus software, doing its thing. It needs to write a quick temporary log file, so it puts one in a shared folder. But, an attacker is watching. And in the tiniest fraction of a second, a split second, before the program can write to its own file, the attacker pulls a fast one. They swap the real file with a fake shortcut. In the Unix world, we call this a symlink. And this little shortcut, it doesn't point to some boring log file. Nope, it points to something really important, like a system password file. The program has no idea. It just follows the shortcut and, bam, overwrites the critical file, potentially wrecking the whole system. So, this whole shortcut swap thing isn't just some clever made-up trick. It's got a real name in the cybersecurity biz. Let's get a little more formal and decode what's known as CWE-61.
Right, so the official definition from the Common Weakness Enumeration, or CWE, is basically this. A program gets tricked. It doesn't handle these symbolic links, these symlinks, correctly, so it ends up messing with files it has absolutely no business touching. The program thinks it's working in a safe area, but that symlink acts like a trapdoor, sending it somewhere totally different, way outside its intended control sphere. The train analogy here is perfect. The train's still running, but an attacker just flipped the switch and sent it down a completely different and very dangerous track.
Now, here's something really important to get. CWE-61 isn't just one single simple bug you can patch and forget about. It's what's called a composite weakness. Think of it less like a single crack in a dam and more like the perfect storm. A whole bunch of smaller things have to go wrong all at once for the attack to actually work.
And this is what that perfect storm looks like. You need all these ingredients for the disaster recipe. First, the program has to be predictable, right? It creates temp files with names an attacker can guess. Second, you've got this thing called a race condition. It's literally a race. The attacker has to swap the file in that tiny window of time before the real program uses it. They have to win the race. Then, the system itself has to be, a little lazy. It doesn't bother to check where that symlink is actually pointing. And the cherry on top? Bad file permissions that let the attacker mess with the file in the first place. You take away just one of these things, and the whole attack just fizzles out.
Okay, so we get how it works, but so what? Why does this actually matter? Let's talk about the real-world damage, because this is where it gets serious.
The fallout from a successful attack really boils down to two big problems. First, there's confidentiality. The attacker could trick a program into reading files it shouldn't, right? We're talking stealing your private data or secret configuration files. But the second one, integrity, is often way worse. This is where an attacker can actually change or even delete critical files on your system. They could corrupt your data, mess with your security settings, or even plant malware and take over the whole machine.
And look, this isn't just theory we're talking about, something you'd read in a dusty old textbook. No, symlink attacks have been out there, in the wild, for a long time. It just goes to show you how stubborn some of these security flaws can be.
I mean, just look at this timeline of real-world cases. We're going all the way back to 1999 with a bug in Perl. Then in 2004, an antivirus program gets hit, just like the scenario we talked about earlier. Jump ahead to 2015 and you see Docker. Yeah, Docker, the backbone of so much modern tech, had a flaw that could let an attacker break out of a container. And it doesn't stop. 2021, a brand new tool gets hit with a variation of this. What's crazy is the scope here, right? From old school programming languages to the bleeding edge of cloud tech. This problem wasn't solved and forgotten. It just keeps popping up in new and creative ways.
All right, so if this thing keeps rearing its ugly head, what can we do about it? How do we stop it? Well, the good news is we do know how. There are some really solid, well-known ways to build up our defenses.
The best place to start is at the design level, with a big picture strategy called separation of privilege. The number one rule here is the principle of least privilege. It's just common sense, really. You wouldn't give a plumber the keys to your entire house, right? You just give them access to the bathroom. Same idea here. A program should only have the bare minimum permissions it needs to do its job, and nothing more. It's also about building digital walls, compartmentalizing, so that if one part of the system gets breached, the damage is contained and can't spread everywhere.
So, what about the developers, the people actually writing the code? What can they do? Well, for starters, lock down those temporary directories. Make it so only the user running the program can even access them. That move alone stops the attacker from doing their little swap trick. Of course, you've got to set file permissions correctly from the get-go. And you know what? Maybe the easiest thing is to just not create temporary files in shared, easy-to-guess places to begin with. Problem solved.
So you might be wondering, how likely is this to actually happen? Well, according to the official CWE database, the likelihood of this being exploited is rated as high. Yeah, high. This isn't some weird theoretical edge case. That rating tells us this is a very real, very present danger that people have to deal with.
And that brings us to the big, lingering question, doesn't it? We've seen this problem span decades, from 1999 to 2021. We know what it is, we know how it works, and we even know how to fix it. So why do our shiniest, newest technologies still fall into the same trap? It seems to come down to a very human problem. In the rush to innovate and build the next cool thing, it's just really easy to forget the fundamentals. Things like checking file permissions and avoiding those tricky race conditions. It's a powerful reminder, I think, that no matter how advanced our tech gets, the biggest challenge is often just getting the basics right time and time again.